plan for today is to wrap up our discussion of logarithms with a few applications. We will learn a little bit about our slide rules today. We'll go back and consider that question of the 12-tone note scale that we posed last time today. And we will also think a little bit about plotting and about log plots and what they can tell us in particular about what we call power law behavior. So for starters, if you've got your slide rule, let's pull those out. And I want to spend just a little bit of time looking at this kind of magnificent device and understand with you how a few of its very basic functions work. In particular, what we want to do is learn how to multiply one of these things. And if you know how to multiply, then obviously you also essentially know how to divide. We'll also look at things like cubes and squares, square roots and cube roots.
Do you have an extra one?
I just brought the one with me today.
This wasn't here on Monday.
Oh yeah, we'll get you one. How about this after class? We'll definitely get you one. I've only got one with me. Now, the basic principle that these slide rules work on is this very simple idea that logarithms turn multiplication into addition and vice versa. So what you've got is log of a product is the sum of the logs. So the very first scale that I want you to look at here, let's start on the outer rim of this device. Let's start here where it says 1. And then let's observe a few things as we go around. So we've got 1.1, 1.2, 1.3, and then going around. Once we've gotten all the way to the other side, we're about to 3. And notice that the spacing is getting a little tighter. 4, 5, and now it's getting really rapid. 6, 7, 8, 9, and then we're back where we started. So we start off with rather wide spacing, and then we come around ultimately to 10 relative to 1. And the spacing is getting tighter and tighter. Now the way that I want you to think about this is, we started at 1 and we came to 10. If I kept going, this would not be 2, this would be, no, what? No? No. Okay, now here's 1. We've got to go all the way there to get to 2, just there to get to 3, 4, 5, 6, 7, 8, 9, 10. Now, when I go to 2, that's not 2, it's, no. Let me ask you another. No. Let me ask it another way. What is to 10 as 2 is to 1? 20. So this is 20, this is 30, this is 40, 50, 60, 70, 80, 90, now 100. Now when I come back over to 2, what is it? 200 and then 300 and 1,000 and so on. So each time I make a lap, I'm going the same distance around. I'm going the same distance around, but I'm multiplying my number. Factor of 10, factor of 10, factor of 10. Do you see how that has this kind of vibe of turning addition into multiplication? And likewise, if we look at a log plot, very similar sort of thing starts to happen. In fact, let's see if we can understand real quickly how it is that the scales, basically speaking, on this slide rule are established. I happen to have my meters today. It's okay. Do it by hand, literally. Now I'm going to label this thing in two different ways. 0, 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8, 9, and 1. That's a linearly spaced scale, normal scale, linearly spaced. What we're going to do is lay on top of this a log spacing, which goes from 1 to 10. What's log base 10 of 1?
0.
Yeah. Let's do a little table. Do a table. Let's do x and log base 10 of x. And I want to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should have noticed I did not start with the scale at 0. Now, log base 10 of 1, we can do that one in our heads. What's the answer? 0. In other words, 10 to the 0 gives me 1. Now, there's another one up here that we can do in our heads, I think, pretty safely. What's that? Yeah. Log base 10 of 10 is 1. In other words, 10 to the 1 is 10. Everything in between here, we might more or less successfully estimate. But let's do it on our little yellow calculators. And on your yellow calculators, the log means log 10, and the ln means log base 10. And we know how to convert to other bases of count. So let's take log base 10 of 2.
0.3.
Okay, go ahead and give me another digit, maybe.
301.
Okay, perfect. And log base 10 of 3.
0.47. 0.4.48.
Okay, great. And 4.
0.6.
6 of?
Yeah.
Okay. And, yeah, okay. 5.
0.6. Well, 0.7.
Give me one more digit there if it's me.
It's rounded.
698.
698? Okay.
Six.
And 6,
7.8.
7,
0.85.
8,
29.0.
and 9.
29.5. So awkward.
Okay, very good. Now, what I'm going to suggest is that on this same scale, we are essentially going to be plotting two things. This is going to be x. This is going to be log 10 of x. The log 10 of x is on the linear scale. And I'm going to start off with x equals 1, which is at log 10 of x equals 0. And then this thing back all the way around here is going to be 10. Okay. Where should I put x equals 2?
0.3.
It's starting to look a little like your slide rule scale. And then x equals 3 is almost up here to the half, maybe there. 3. 4. 5. 6. 7. 8. that works? Very good. Now, if I wanted to multiply two things, so for example, if I want to multiply x times y, then I could write it as follows. I could take log x plus log y, which would be log xy. And then I could say 10 to the log x plus log y. So in a nutshell, what I'm doing is I'm computing the logarithms by reading across this scale. Then I'm adding values on the linear scale, and then I'm reading back across in the other direction to do the multiplication. Let me show you a little bit more specifically what I mean by that. So let's try something we know how to do. Let's try 3 times 4. And I think that we can do this in just a second on our slide rule, but let's do it on our sort of big slide rule that we've made up on the board here. In fact, let me pick two numbers that are a little different from each other, even though they'll stay in their same cycle. If you don't mind, let's pick 3 and 2. That'll work real well. Okay, so 3 corresponds to this length. In log space. Okay. 2 corresponds to this length in log space. But I want to take 2 and tack it onto 3. Then I convert back out of log space. My answer, which is 50. So we took the value we were interested in, took its log, which puts us on the linear axis, either 3 or 2. Then I added log 2 linearly to log 3, and then converted back, reading across in the opposite direction. Is that cool? That's how we got to the video. More or less. There are several other nifty things that this slide rule will do. In fact, let's practice with that a little bit. If we were to do exactly, for starters, that same operation on our slide rule, how would we do it? Well, let's start off on this scale here. And we're going to turn our inner wheel. We're going to turn our inner wheel to 3. So our outer scale is going here to 3, and I'm going to line up the pointer of the inner wheel with 3. Then, on the inner wheel, I want to go forward to 2. I'll take the slider to do that. Move around here to 2, and then read back out, and I'm right on the sides. And then one can reverse that operation to do division. Everybody get it or not quite yet?
Did you say?
Yeah, let's say it again. Okay, so let's start on the outer wheel at the pointer. We're going to stay on the outer wheel and work our way around until we get to our first number, which is a 3.
Is it blue or orange?
Right there in blue. The orange on this slide rule are things that are red that increase in the counter direction. The blue are things that increase in the forward direction. So we're going to go to the 3, okay, and then I'm going to line my pointer on my second wheel right up with the 3. Now I'm going to read forward, not on the outer wheel now, but on the inner wheel, from 1 out to 2. And I can line this up to read across, or you can just read across without it. from 2 back to the outer wheel is 6. Yeah, okay, good. So you've got your inner wheel lined up with 3. Now take the pointer around to 2 on the inner, and you're back to 6 on the outer. Perfect. Okay, that's our slide rule for multiplication. Now this slide rule will do several other things for you. The next thing that it does, which is nifty, is that it will do squares and cubes and logs. Well, squares and cubes for now. Let's stick to that. Squares and cubes can be done using only the inner wheel. You don't need the outer wheel. But let me show you the magic of the squares and the cubes. So looking at the inner wheel, at the outermost dial there, we go, same way, 2, 3, 4, 5, 6, 7, 8, 9, 10. A factor of 10 going around once, right? Now, do you see the little line there that says square? Follow it. 2, 4, 6, 9, 1, and then it got halfway around, it's all the way to 10, and now it's counting from 10 to 100. So one trip around is a factor of 10 for the regular wheel, but one trip around is a factor of 100 for the square wheel. Make sense? Now look at the one that says cube. How many cycles does it make when it's going around once? 3, factor of 1,000. So on the cube, here's 1, then here's 1 again, which is now 10, and here's 1 again, which is now 1,000. Sorry. Here's 1 again, which was 10, 1 again, which is 100, 1 again, which is 1,000. Does that make sense? So you can read right across. Let's find something again that we know how to take a cube of real easily. Let's go to on the inner wheel, at the outermost dial, the outermost gauge of the inner wheel, let's go to 2. And then if you just read down across those others right below, you should see 4 and 8. 2 squared is 4, 2 cubed is 8. If we go to 3, then you'll see 3 squared is 9, and 3 cubed is, it's between 2 and 7. So what does between 2 and 7 actually mean in this context?
27?
I mean between 2 and, between 2 and 3, actually, yeah, it means 27. It's a little closer to the 3 than to the 2. So one thing you've got to watch out with your slide rules is that your slide rules make sure you know how to do the decimal point already. Because a lap is a factor of 10. You've got to take that into account mentally. So what the slide rules were for, the people that were using the slide rules, they already knew how to estimate things really, really well, better than people do these days, generally speaking. So in other words, you could kind of round numbers off a little bit so that you could get a general estimate of what the multiplication would be. But the slide rule was for what? It was for getting a few decimal points of accuracy when you already knew the basic answer. So if you already knew that 3 cubed should be in the ballpark of 30-ish, and you saw something between 2 and 3, and it was at 2.7, actually, you would slide the decimal point. And the same thing as you go a little farther around. If we go to 4, that thing's actually going to play out twice. So 4 squared, well, if we go to our square wheel, we're between 1 and 2. In fact, we're at 1.6, which we should read as 16. And then 4 cubed, we're between 6 and 7. We're actually at 6.4, which we should read as 64. Good. So that's how our slide rules work. There are several other things that this slide rule will do, including exponentiation and logs and sines and cosines. It will even actually do something nifty on this outer wheel. It will do conversions between what are called natural units or Planck units. It's sort of a neat thing we threw in on the outer wheel. These other functions are simultaneously a little more complicated and a little less interesting. In particular, the trig functions, for the most part, just correspond to, we marked angles as you go around, and then on another dial, we marked the value of the trig function. So it's just basically a table where you would read across, but you could read across the table using your slider. It's a little less interesting. The log and exponential wheel here on the interior is very interesting, but it's also a little bit complicated. But if you would like to play around with those other wheels, there are very concise instructions on the back there for the way each of them work. Now, the next thing that I want to talk about for just a second is log plots. Again, all of our log plot axes look pretty much like this. In fact, you'll find that when one is doing log sampling, a very common spacing to take. Do you see that each of those spacings is, they're not perfect, but they're more or less similar to each other? If one is doing sampling, for example, in a log space, a very common thing to do is to choose 1, 2, 5, and 10. These are very typically the marks that are set up on log plots, even if one doesn't want to do all 10 marks or anything or subdivided by that. What I mean by sampling, for example, is imagine that you had some function which existed in a complicated plane, and you could do a calculation. But imagine this calculation, for example, was really expensive. What I mean by an expensive calculation is that your CPU has to run for a finite, measurable amount of time in order to give you an answer. So say you wanted to do a contour plot of this thing. You know what a contour plot is? Like in 2 dimensions, the contour plot is like a topography, a topographical map of a place. So if you had a mountain here, you say that's the mountain, and this was all at the same elevation. This was all at the same elevation, but maybe there was another slightly less tall mountain over there, and then the river kind of ran through there. So these could be in different colors. And everything in this region is at one elevation, and this or other elevation. It doesn't literally have to be a map of a physical location. It could be a map of some parameter space you're interested in. So say, for example, it might be something like the contour I've drawn is not necessarily accurate, but this is a physical situation that's relevant in neutrino oscillations, something that's actually related to some work we're currently doing with Professor Dent. And this is different types of neutrinos, how much they mix with each other. And this is the separation in the mass square of the neutrinos. And within some parameter space, you might be interested in finding out how well a certain experiment could detect this scenario, if that were the scenario that nature chose we were looking for. So you might want to tell, for example, how well nature's ruling out each of these scenarios under a certain experiment. Given a certain amount of collected data at a certain experimental site, how confident would we be that nature was not doing something at this location in the parameter space if we did the experiment and didn't see clear evidence of something unexpected? Now, in this particular case, typically you want to span lots and lots of these things. This horizontal axis is telling you how strong the effect is. And you want to span lots of possibilities from little tiny effects to rather large effects, for example. And the same thing for the mass gap. So each of these ends up being a log type scale. So each of these steps are factors of 10, let's say. And you can run a computer simulation. To calculate how confidently a certain experiment would be capable of excluding that possibility. And a lot of times that's what you want to project in an experiment. You say, there's something we don't know what the value is, but if it were this value, would my experiment, even if it saw nothing, have been good enough to rule out that value? Right? If the effect was really small, your experiment can't rule it out. You say, well, we didn't see anything, but the effect was so small, it was within the margins of error. We can't rule it out, right? You say, oh, the effect would have been this big, and our margins of error were this big. You say, okay, I could have ruled it out. So that makes sense. Something like that. But this is an example again where the spacing is basically factors of 10. Now I want to do things which are very, very small and then also substantially large, for example. And I want to put all of those things on the same plot, so I need a log plot. So how should you space your sampling? You're going to have to space lots of points in this. You're going to have to sample lots of points in this plane in order to draw the topographical map. But each computation you take may be a very, very extended computation. It may take the computer a few seconds for each computation. That sounds real expensive, but if you need to sample thousands of points, and you need to maybe do that lots of different times or for different scenarios, these things really add up and they multiply. So let's say if your calculation takes a few minutes, then you're really in danger of that becoming unmanageable if you have multiple axes to scan across. Right? So how should you space your points? Well, if you space them linearly, you'll have a disaster, right? Because you'll have lots and lots of points down, I should actually say it the other way. You'd have lots and lots of points up here, and then you'd end up with almost no sampling down here, for example, because the spacing down here is actually tighter. And if you were taking linear steps, you would have just skipped over all the interesting stuff here. So what might you do? Well, if, for example, this is a factor of 1, this might be a factor of 0.1, this might be a factor of 0.01, and for example, if you make that more or less evenly spaced, this would be something like 0.2, 0.05, and 0.1, and then 0.2, 0.5, 1, 2, 5, 10, and so on. And for example, you could use those as your tick marks, or even if it suited your need, you could use those as kind of your sample points. If you needed more dense sample points, you could obviously work out something that was a little more densely spaced, but using that same basic paradigm. Makes sense? I want to space my sample points evenly in multiplication space, but not in addition space. One other thing I want to show you about log plots that's very nifty. Imagine that we had a plot like this, where what we were plotting on the horizontal axis was not x, but log x. And what we were plotting on the vertical axis was not y, but log y. Again, that's basically what we've done here, right? In other words, log 10 of 10 is 1. Log 10 of 1 is 0. Log 10 of 0.1 is negative 1. Log 10 of 0.01 is negative 2. So we've turned our linear space into a log space. Imagine that we had something like this, and we had some data that had been collected from something which we wanted to measure. And imagine, that within some statistical fluctuation, those points ended up basically on a straight line. This is a very common scenario, and it's an incredibly useful scenario, as I want to show you in just a second. It's a very common thing if you have particularly a function where you don't really know how y depends on x, but you want to figure out how y depends on x. One of the niftiest things that you can do is, instead of plotting y versus x, plot log y versus log x. And in particular, if after doing that, your points end up on pretty much a straight line in that log space, there's something really powerful and interesting that it has to tell you. Now, let's look at that. So let's look at that. Let's imagine we take the slope of that line, and we have delta log y there, and we have delta log x there. So a difference of log x values and a difference of log y values. We measure that slope. Okay? And let's say, for example, this looks like a slope. That would be a slope 1. The way that I've drawn it, that slope is pretty close to 1, just a little bit less than 1. This might be a slope of 2. This might be a slope of a half. I don't remember what slope is. What's the phrase that they say for slope?
Rise or run.
Rise or run. Still say that? Rise over run. How much did you go up versus how much did you go over? So for example, this would be a slope of 0. This would be a slope of -1, -2, -0.5, +0.5, 1, 2, 10, infinity. We're good. So let's imagine that we had some slope here. So we've got delta log y. What does that mean? Well, it means log for example, let's call this point A, and point B. So delta log y is log y
You want to say?
b minus log y a divided by delta log x, so the difference in log x values. So that would be log x at point B minus log x at point A. And let's imagine we take that slope and we measure some slope. We'll just call it S, we can call it M if you like. Some slope. In fact, we'll say something about that intercept also in just a second now. We've got this difference of logs. The difference of logs can be written as a log of ratios. So we can write that as S is log YB over YA over log XB. You bring this up to the other side. Say S log XA over XB is equal to log YA Now we can do something else. This S, you see the S sitting out in front of the log? What's the operation I can perform? We usually think of it the other way, but I can go both ways. If the S is out in front, what can I do? Can I raise it up there? So I've got log X over X A to the S. Thing inside the log, but this is up to the power S, is log YB over YA. So I've got log of something equals log of something. What can I do next? Take out the logs. If the logs are equal, the things are equal. In other words, if you want to be a little bit more formal about it, I could exponentiate both sides. If these were log-based 10s, I could raise both sides to an exponent of 10. To say it very simply, if the logs are the same as each other, then the things are the same as each other. So I've got XB over XA to the S. YB over YA to the S. In other words, what it tells me is that I've got a power law relationship between my variables. y is related to some power of x. In other words, if this slope was 1, then I'd have also gotten a straight line if I plotted them on a regular plot. It would have still been a straight line because they have a linear relationship. If this slope had been 2, if I had just plotted y against x, I wouldn't have seen a straight line at all. What sort of curve would I have seen? Yeah, a parabola. If the slope turns out to be 3, then y is related to a third power of x, and so on and so on and so on. So, for example, if you hypothesize that you have two variables that might be related to each other by a power law, but you don't know what that power is, a fantastic way to figure out what that power is to plot both of them on a log plot. Let me give you an example. I don't know if this is exactly how it was done historically, but let me tell you a neat example, which has a very interesting and a very unexpected power law behavior. From a modern point of view, one can actually prove this using Newton's ideas of motion very, very quickly. But at the point in time that this was first discovered experimentally by a fellow you've surely heard of named Johannes Kepler, it would have seemed very, very strange. And there was no underlying notion, theoretically, for where this would have come from. What Johannes Kepler found out is that the farther away you are from the sun, the more time it takes to go around. That's probably not too surprising. But there's in fact a very, very specific relationship. If you take your distance away from the sun and you cube it, and we're assuming the orbits are more or less circular, but the law still applies if they're not circular as long as you transition into something like an average radius, or what's called a semi-major axis. So if you take your distance away from the sun and you cube it, and you take the amount of time it takes you to go around the sun and you square it, those two things are going to be identical to each other. So let's do a few examples of that. Later in the semester, by the way, we'll know enough math and enough physics related to the math that we can prove that that's true in literally about 3 minutes. Johannes Kepler spent 40 years of his life trying to figure this out based on the observations of an astronomer who had been his contemporary, who died somewhat before him. Yeah, you got it. Tycho Brahe had been sort of a mentor to Kepler and lived basically during overlapping lifespans. He was a little older and had died. And his dad went to Kepler. And Kepler spent 20 years of his life, let's say, trying to figure out this principle. And from a modern point of view, it can be derived with present physics and not physics, which is fantastic. What a testament to the progress of knowledge, right? And furthermore, Kepler, when he worked it out, he knew that it was true based on observation, but if you had asked him why, what kind of answer could he give? So we'll learn why it is later, but for now, let's just take it as a rule. It's Kepler-Meyer. And in fact, let's use some special sort of units here to make this very convenient to work with. So if we're talking about planetary orbits, and we're a little parochial, a little concerned with our own point of view, what would be the most sensible unit of time for us Earthlings to use? Years, because that's how long it takes to go around the sun. And we could also measure distances from the sun in oh, good. Yeah, you know the specific name for it. That's the idea. In multiples of our distance from the sun. There's a name for that. It's called AU. That's perfect. So, in fact, if we agree to measure that in years, and we agree to measure that in AU, at least numerically, we can draw an equal sign between those two things. Now, this will also be a nice little exercise to use our calculators for a second to make sure we can invert expressions of this variety, for example. Let me give you some information. And this is just approximate, okay? These things are highly rounded so that they can be remembered a little bit more easily. Let's say distance from the sun for, let's say, Saturn, Jupiter, order there, Uranus, Neptune, Pluto if you like. Jupiter distance from the sun is about 5 AU. Rounding these things quite a bit. Saturn is about 10 AU. Neptune is about 30, and Uranus is about 20. We don't need to use our logs to invert this equation. We just use simple roots. Well, let's invert this equation, get some ideas of the times. And then actually, I think what would be a really neat exercise is to, once we've kind of seen how this works out, actually take the tabulated data, plot it log, take the slope off of it, and recover Kepler's third law here, with proportionality based on the observed data. I think that would be a good thing to do. I think we might actually make that a homework assignment coming up pretty shortly. But let's see if we can figure out what these times are. So all we need to do is get our calculator. We don't even need to use the logs here to understand the log plot we need our logs. This is just a simple square root. So what I'd like for you to do real quickly is to cube these things and then take a square. These small ones we could probably more or less do in our heads. 5 times 5 times 5, what's that? 125? Can you think of a number whose square is in the ballpark of 125?
14.
Over there.
You said bigger, 125.
Yeah, one in the ballpark of 125. Well, what's 10?
11.
Yeah, 11 is in the ballpark, between 11 and 12. Yeah. I'm rounding a little bit. In the spirit of the rounding, I think 12 is actually closer. Both those numbers are rounded a little bit. Saturn, 10 times 10 times 10, that's 1,000. Can you think of a number whose square root is about 1,000?
30?
Yeah, ballpark of 30. Yeah. Saturn takes about 30 years to go around. Jupiter takes 12. By the way, I haven't seen this in a long time, but I used to see, if you go to a Chinese restaurant, did you ever see the Chinese zodiac signs laid out on the placemat? How many signs are there in the Chinese zodiac? Well, you know why? Jupiter takes about 12 years to go around. So what the signs of the Chinese zodiac are positions. I have to fudge a little bit, but more or less. They're positions of Jupiter, which looks to the naked eye like a really bright star, but one that moves relative to the constellations. What constellation is Jupiter passing through, for example, in the year that you're born? And this cycle's about 12 years, so the Chinese zodiac is 12 years. If we take these others here, I might put that in our calculator, 20 cubed and then square root, what do we get?
8,000 for the cube.
Okay, and then square root?
$89.44.
It's getting pretty hefty. You might get to see Uranus go around once in your lifetime. Neptune, 30 cubed, and that's square root. And then Pluto is about 50, about 40 AU, give or take. But it has quite an eccentric orbit. It actually, this Earth comes passes inside Neptune. See the beautiful pictures back from Pluto last year? Gotta look that up. We have really nice pictures of Pluto now that we never had before. I used to really be in favor of kicking Pluto out of the planet family. I thought it was a great idea. Listen, this oddball, eccentric orbit, he's out in the Kuiper Belt. There are other things that are bigger. Once you see these Pluto photographs, though, you really want to just apologize. Let's tack this onto our homework. I think this is going to be fantastic. So let's close with this for today. Let's tack this onto our homework. What I would like for you to do is for all 8 planets, or 9 if you like, Find their average distance from the sun in AU, and find their orbital period in years. Then I want you to get some graph paper, or you can do it in Excel if you like, or you can do it by hand on graph paper. And I want you to then take the log. You can use log base 10, you can use whatever log you like. Log base 10 is fine. Take log base 10 of all your average distances from the sun. Keep that in the table. Take log base 10 of all your cycle times, and then plot these values versus each other, whichever one you choose for x or y. It doesn't matter. It'll just flip your slope upside down. And then calculate the slope of that line. If you do it in Excel, you can use their regression fit. What you should find by the time you're done, depending on which way you did it, is that your slope is either 3/2 or 2/3. So let's add that to our homework list. And let's make all of these things do along with that, let's say Friday next week. I'm going to hit you up with another assignment on logs before we get to that, so there might be a couple of them. Okay, any questions for the day?
Yeah, can you repeat that?
Yeah, the whole thing?
Yeah.
Sure, I'll repeat it. So for the homework, find a table on Wikipedia or whatever you like. Find the 8 planets or 9 planets if you like, or you can add Halley's Comet in if you like. Find their average distance from the sun in AU. Find their orbital period in years. That should be a table, right? Then build a new table that's log 10 of all of those. If you do it in Excel, you can do it super fast. Build a new table that's log base 10 of all of those. And then on one axis, plot your log base 10 of R. And on the other axis, plot your log base 10 of T. And then find the slope of that line.
So an average distance from the sun, AU, plot the rotational distance?
So you've got 2 variables, distance from the sun and time.
Okay.
Plot the log of the distance values versus the log of the time values.
Okay.
Yeah. Log of distance values versus log of time values, and then take the slope. You should find those 1/2 or 2/3 if you do it that way. Okay, have a great weekend. See you next time.
Your first efforts say you can use Wikipedia.
I like Wikipedia. Wikipedia is amazing.
English teachers don't like it because it's so easy.
Well,
It's also really hard, it's really easy to get lost on it, because you go from one thing to the next.
the more technical a topic is, and the less likely it is to be prone to interpretation of politics, Wikipedia can be fantastic.
So like for math.
Oh, it's amazing.
Can I say that?
But if it's like, history, it might be a little too deep or too.
Well, history's always that way, but even in those cases, the people that end up winning those moderation fights are probably the ones that have reasonably conventional views.
Right. I always wonder, like, if you took a subject and asked somebody their opinion based on like where they are in the world, like for instance, opinion on America from Americans versus Europeans.
Yeah.
Like